Hello, everyone. Thank you for joining us today for a Rigaku topic webinar. So today we're very pleased to be introducing you to our new source, which is the PhotonJetMAX-S. This is a new high-performance microfocus X-ray source that we've been developing. So I just want to point out that you can ask questions throughout. We expect that this webinar will last around 30 minutes. We're aiming to finish by 3:30, and depending on how much time is left, we will take some questions from you. So please feel free to use the Q&A button to ask questions as you like. Please also join our forum, so www.rigakuxrayforum.com, where you'll be able to find the latest information from us on subjects like this. Just before we start on today's webinar, I just wanted to make a little plug for the next webinar. So this is in 1 week's time, and our speaker will be Dr. Maxime Siegler from Johns Hopkins University. So please do join us. He will be talking about our rotating anode product, the Rigaku Crystal Lab Synergy R. So you can register for this by going to our website and finding the relevant entry in the events calendar, which is under resources. If you're already an attendee of this webinar, you don't need to worry, you will be sent an email soon to register. Okay, so let's get on to the topic of today. So I'm joined today by my colleague, Dr. Jakub Wojciechowski, who is a senior application scientist in our office in Frankfurt. So I will pass the floor over to him in a short time. I'm just going to do a little bit of an introduction to what the source is before I pass on to Jakub to discuss some results from this testing that we've done. So the PhotonJetMAX-S, as I've said, is a microfocus sealed tube source. It's designed for high performance. It's offering about double the intensity compared to our PhotonJet-S, which is the current sealed tube source that we have. And the operating costs are the same. So Jakub will tell you a little bit more in a while about the performance improvements. But generally speaking, if you were to have this in your lab, it wouldn't cost you any more to operate than having the PhotonJet-S. So as I said, the PhotonJetMAX offers more flux to your sample with more than twice the diffracted intensity. So photons are arriving at your detector, which have been diffracted from the crystal. And this is made possible by increased capture of photons from the X-ray tube using proprietary Rigaku optic technology. So what do I mean by that? So we have a diagram of the two sources here. So you can see that we have a longer optic, which is capturing more photons, but also the optic is capturing more output from the X-ray tube. The tubes that are in this source cost the same as the tubes that are in the PhotonJet-S. So you don't need to worry about breaking the bank to find money for expensive tube replacements down the line. And we run at the same wattage as the PhotonJet-S as well. So it runs at 50 watts as well. So it's just as eco-friendly as the PhotonJet-S. And the tube lifetime has proven to be quite long for the PhotonJet-S as well. So similar tubes in this source also expected to last quite long. The PhotonJetMAX-S also features our patented divergent slit mechanism by default. So this allows you to have a best of both worlds when the optic is converging on the crystal, you will sometimes see overlap with reflections which are very close together. Our divergence mechanism allows you to trim the divergence down so that these reflections become separated. So I'll just play that movie one more time so that you can watch what's happening. Get it to reverse back to the beginning. Doesn't seem to want to play again. Okay, here we go. So if you watch down in the bottom corner here, you can see the effect of closing the divergent slit on the overlap of two reflections which are adjacent. So this allows you to be able to study samples such as proteins or twins or powders with more flexibility. So you can tune the divergence to exactly the level that you need, preserving as much intensity from the source as you can. And in our sources, the vacuum path extends almost up to the collimator tip here. So you have there's not as much loss through absorption from the air of the beam coming out to the crystal. Okay, so what does all this mean? It's nice to talk about features and specs, but what is much better is to look at the actual results that you can get from these sources. So at this point, I will pass over to Jakob, and he can tell you a little bit about the experiments that he's done to show what this source can do. So Jakob.
Thank you, Fraser. Just give me a second to snatch the screen out from you. Okay, I think that was the slide finished.
We're looking at your presenter view, Jakob.
Sorry. Share it again. I feel like practice before and failing on the. Okay. Okay, I think now we have it working. Sorry. The smoothest transition. Okay, so basically what Fraser said, we could summarize with 2 slides, and this is like pushing the limits of data quality, and you can see some average important statistics for the test that we did. So showing this improved performance in just diffracted intensity, so amount of the photons that you're getting from your sample, and also the similar to noise, of course, because you have a stronger data set, you will get better R-int, that getting better R1. And we also did the test just to check how much you get better data when you're doing protein crystallography. And of course, we're observing similar effects, so better observability. But that will be too short for the topic webinar. So we want to shine more light what we actually did, what kind of application tests we did, and why and how. So this is why I'm here. And sorry, it's a different slide. We want to show you the because the spec doesn't always tell all the story. We want to show you how we did the presentation, how we did the test, and I want to tell you how we select the samples, what kind of samples, and what kind of at the end performance boost you can expect in different application scenarios. And those will be the rest of the slides showing results from those tests that I was asked to do when we were working with R&D. And we set up the objectives for those tests, and the biggest part was to just translate the hardware specs of new hardware to measurement performance and check how it integrates with the whole system to see how much performance you're getting as the whole system altogether, and then provide some easy unbiased numbers that I present you on those 2 slides. So selected objects. So some examples of them. So we started with citidine. It's Rigaku standards. I like this crystal because we have access to nice good crystals that cut easily. So I can make the same from the same crystal, basically the same batch, different size of the crystals. So you can see I made myself a crystal which I would call the standard size, which required me to use just around 1 second of exposure time, a smaller one, which we call the small size, and then something that we call already rack or rotating allot size, which needs another bump in the exposure time up to almost 10 seconds. So, And of course, we have not used only the standard crystal because that would be quite boring. We use also other crystals with a different, harder morphology, let's call it like this. Taumatin that you have seen as a protein example. Also, you use suborganometallic system that crystallizes in triclinic system. And going to the protocols, the whole idea was to collect exactly the same data sets. So we have been using, you see my test R&D source looks completely different because it was still R&D prototype, but we used exactly the same tube. We just switched the sources. The rest of the instruments stay exactly the same. We took care to remount the crystals exactly the same way, so we could use exactly the same scads. You can see that I was able to check the Chrysalis Pro, that I was able to remount all the crystals in the same way, with the difference of orientation of the crystal of the goniometer being basically not meaningful to change of how the data is collected. And also in processing, this is the time when you don't use auto processing built in Chrysalis Pro, of course, and you can adjust and test all the options which there to make sure that only the one that doesn't affect any of the data set or only provide benefits are used correctly. We scale that at the same thing. We have also inside tool that allows us to create the same sets of HKLs, so we compare exactly apples to apples. When possible, I use, of course, Nosferatu to use the best model to fit data to get you the idea how the data improves much. I also want to use that we strongly use the value which is F square, or sometimes called F2. It's a normalized intensity, well, normalized corrected to 12 seconds per degree, and you will see that numbers a lot on my slides. We don't use it very often in general crystallography, but it's very useful when you're doing such a test. So results from the test. So here are the crystals that I measure, and I allow myself to calculate something like the relative volume between them. So you can see I select them this way, that the smallest one that you remember is 1, then the B will be 5 times more volume, and the A will 10 times volume. And what we observe in all cases, improvement in photons that we're getting from experiments, implemented that those are the same scans, the same sets of reflections. So those are really apple to apple comparisons. We see, of course, because we have more photons from the diffracted photons from the crystal, we see improvements in the I2 sigma, the R-int goes better. And of course, the refinement improves also if you have a data. As I mentioned, the crystal C is already rotating anode crystals, so I didn't really have a time to collect a proper data set. So we use it to collect a very weak data set, as you can see, all around 3 I2 sigma, which is only possible because we're using high-peaks detectors, so we can trust this data so good that we can collect such a weak data set and still use it for the tests. So the other experiment I did with one of the cyclic crystal, it was just getting different experimental conditions, different redundancy, different strategies on both sources. So this is table showing for the different distance. And what I was up to achieve is to get those numbers, basically this percentage, how much getting I2 sigma boost. And this was important for me because if you are a Chrysalis Pro user, you will know that you can use that later to calculate very quickly the difference using our software at Chrysalis Pro if you get this average number. And let's say I average it slightly down, and I was using in those simulations, which you see later, a 150 percentage increase in through the different scenario of data collections. I almost always saw above 150% improvements in the process data the same way on the same scales I2 sigma. So we of course didn't stop just looking on the Chrysalis Pro results. This is one of the refinement of using the cytidine crystals, and you can see that we use a tool to set up the files that have a common set of the goals. You can see that the refinement is on a similar set of diffraction. I don't know, it's probably copy error here, but it is the same set of the reflections. We can see that bump of intensity that I was reporting earlier, and we can see that the model improved more. So if we measure the same crystal on new source PhotonJetMAX-S, you can really push the quality of the data from something that had basically not trustful absolute structure. We could say that, okay, we're getting there already close enough to publish it. And then this is example what not to do at home. So small weakly diffracted crystals mounted with the significant amount of oil to reduce the influence of the background. And we again collect a very weak data set, and we want to check how much we're getting from improvements on a weak data set and observability of the weak data hidden in the background. So again, we can see that we're observing much more photons for PhotonJetMAX. And of course, I2 sigma also improve it, and it's not only on the low angle, like on the low angle, but also the high angle. And what I like to see the more is that I got improvement observability, so average I2 sigma, and then reflections, more reflection above the free I2 sigma limit around that 1 angstrom, which was the goal of the test, showing that if you struggle to solve some crystals, you know that getting those data observable around 1 angstrom from weakly diffracting samples from both crystal that doesn't want to diffract is a key to actually be able to solve the structures. And you can see that the PhotonJetMAX-S outperformed the PhotonJet-S, providing more observable data around 1 angstrom and providing data set that is much easier to solve. Of course, this data set was not collected to publication results, but I still want to show you that on the same amount of the reflections, we have 76.8 reflection, which comes from larger than I2 sigma, larger than test to 2 compared to 625, and just statistics that are in this lower, so no loss to the data quality integrations, higher I2 sigma. This is what I want to also see on the higher performance source. And that test was done mostly to test our divergence control device integration in the source, but we use it also to just observe the data, and we can see better observability on the data set. And after tuning the divergence slits on both sources, so basically I had exactly the same image. So you can see this is like a full first attempt without touching divergence control, and this is how the image from protein crystallography for the protein sample should like. So nicely separated spots. We're using both divergence control and our kappa goniometer to orient the sample to provide the little overlaps. So both data sets have 0 overlaps pixels, and we still see slightly better observability, and the last shell has slightly more photons. Even if I tune both sources to provide exactly the same diffraction images, showing that the beam is still performing better. So let's go to this test that I want to show you how it actually performs and what are benefits for you in a normal ride. So remember the test that I showed you that I was talking about getting this average I2 sigma from different conditions. So because I can have that, I can now use our built-in Chrysalis Pro simulator to simulate you some data sets, because I know the relations between the sources. So I know how to set up the simulator for both of them. So I can just simulate in minutes multiple scenario for your measurement. So that's a standard measurements what you would did on this standard cytidine crystal. and you will see that 20 minutes to 45 minutes doesn't feel so bad, but let's just switch our data collection strategy for monoclinic sample, which is the point group. So basically chiral monoclinic crystals. Let's assume there is no anomalous signal. So let's put a redundancy 8, and you can see that the same ratio states, and it's 2 hours versus 5 hours. And then you start seeing the benefits of high performance sources in your lab when you start operating for the samples that are challenging for even modern instruments to collect, just because of the amount of data you need to collect. But of course, you can use it also to just collect better data. So at the same time that you would collect the same crystal at the PhotonJet-S in 45 minutes, on PhotonJetMAX in 45 minutes, you either can collect much more intense data, so 2398 from the simulator. So if you go back to the slides, you will see that it matched the results that I acquired from the test, or you can just keep the same intensity of average intensity of your data set and just change from 5 to 12 redundancy, whatever is your preferable method of improving your data set quality. And what I like the most, this is not very, I would say scientific, but plot, but I can show you that this diffracted intensity angle, which is coming down with the relative size of the crystal, is slightly elevated. This is larger angle than compared to the PhotonJetMAX. So it allows you to measure smaller crystal faster with better observability of the weaker reflections. So why measure smaller crystals? Like lots of people ask why you want to measure smaller crystals, because they often will have a better quality of diffraction. They will not provide you lots of larger objects will already have twinning, when smaller crystals can be found without the twinning. They often will give you higher resolution because they will have less defects inside them. And often it's because you are just lazy and then you want to recrystallize the sample to get to the proper size. And we observed that the data set on several samples, small volume samples, that data is much more better with observability. So from summary, double the intensity, same cost operations, and you can collect much faster or better data from routine crystals, start measuring smaller crystals, and so solve finally the challenging crystals that were stuck around this one angstrom barrier. Now you can confident even try to get the solution from those crystals that should go for rotating anode or synchrotron, but you may try it again on the new source if you get more data, better data from our PhotonJetMAX-S source. And that's basically all. I hope I keep with time with all the problems on the beginning.
Thank you, Jakub. Sorry, that was a little faster than I expected.
Okay.
So I took the decision to answer questions by typing while you were talking, which means that we don't really have any left except for one. So maybe to answer this, I'll just make some general comments. So for the time being, we only have PhotonJetMAX available in copper. We're hoping to introduce other wavelengths sometime soon, but for now it's copper. As far as upgrading goes, we are hoping to offer upgrades, but please do contact us if you're interested, as there may be some configuration in your particular system that we need to consider. So contact your local sales representative. PhotonJetMAX will be available to probably from the very end of this year, beginning of next year, to start shipping. So if you are interested, contact your sales representative. There's a little time that you have between now and then to get things in order. Okay, I don't think there is anything else I wanted to say. Jakub, do you have any?
If there's no questions, sorry for making this so fast. I probably panicked from the beginning, making it losing so much time to set up the presentation and switch to the second gear. So I hope that it went through. not too fast.
Okay, there's maybe a general question that you could answer here. It's more about experimental technique than the source itself, but for a crystal with high decay, what is a good value for the redundancy?
So like high decay speed, good value for that. So depends what you mean high decay speed. So if it's surviving to collect your complete data, just leave it there and forget about redundancy. Usually when you see the scaling clock dying, it's better to not add it. It will not add you better data. We scale the data. You can use the decay function, so at additional scale to get out the data. But the whole idea of adding redundancy to your data is to lower the errors on the measurements, so basically sigmas. So if you already introduce extra scale to scale the intensity to the one that you measure on the beginning, to the one that you measure after you hit the completeness, and just adding redundancy, actually benefits of this redundancy are not as good as normal thing. So I would say that just try to get the complete data set as fast as possible with the minimal requirement to hit the quality of what you want to have for publication of your crystal. And that's all. So if you have limited time that crystals survive, and the resolution is problem, that you lose resolution, I would say it's better to collect 2-3 crystals with higher intensity to get the resolution going better and merge them together, rather than trying to achieve that by remeasuring the empty frames multiple times and hope that the statistics will improve. Because at the end, information will be not there, and you cannot extract, even on high peaks, you cannot extract intensities from empty frames with background only.
Yeah, I'd maybe just add to that, it does depend on the reason for the decay as well. If it's X-ray damage, then there's not so much you can do. But if it's some other reason, having a high intensity source and a big detector like the Hypix ARC 150 can help you get as much data as possible before the decay happens. And as Jakob said, there's no point in trying to add noise into the data set by collecting something which is already decayed just to increase redundancy. Okay, I think there's another question from David. Can we increase the scan angle for each frame to get full data in time? I'm not sure what he means by that.
I think that it's connected to all detectors.
I think he means wider frames. I think he means collect wider scan frames.
Yes, when you had the readout time between the frames. So I would just assure you, David, that all the Hypix detectors cooperate with completely shutterless mode with almost zero dead time between frames. So fine slicing the experiment or extending to wider frame doesn't really matter. What you have to care about is to make sure that the reflections are collected in the way that the processing algorithm can handle them nicely. And for this, you don't have to worry, because Chrysalis Pro will adapt the strategy for you, looking on the reflections during pre-experiments and adapting this for you. But there is no connections to the scan range and the time of data collections anymore on the detectors that are HPC detectors and have a true shuttleless modes. So you don't have to worry about these settings anymore in the modern instruments.
Yeah. Okay. Thank you. Okay. So with that, I think we'll call time. So thank you very much again for joining us. If you're interested in this source, please, as I said, do get in touch with your local sales representative. We hope to be able to offer demos for this source in the next few months. So if you get in touch now, then you'll be able to get into line. So thank you very much, Jakob. I appreciate your help on this, and thank you everyone for joining. We'll see you next time. Goodbye.